Greetings! In today's video, I'm going to show you how to sign cookies using HMAC in the Go programming language. My name is Karol Moroz, and you are watching Make Programming Fun Again. Yesterday, we built a simple storefront page, and the natural next step is a shopping cart. Alas, we can't build a shopping cart without a way to persist state between requests, for example in a session store. There are many ways you can secure a cookie to at least ensure they cannot be forged. You can use an HMAC with a shared secret. You can use an asymmetric signature algorithm like the ECDSA algorithm used by the Bitcoin protocol, or you can use a construct called authenticated encryption with additional data, or AEAD in short. In this video, I'm going to use HMAC because it is the easiest and the fastest of all of the above. If you are new to this series, you can download the source code for the project at github.com/moroz/kinenomichi, and I'm going to add a link in the description below. And we are going to be using Stretcher Testify, which is a testing library for Go. I'm going to start by installing this. Go get this library. And I'm going to open the project in the code editor, and inside this lib directory I'm going to create a new directory called cookies, and we can I will start by defining an interface. So in this package cookies, I'm going to define an interface called session store, which is an interface, and it's going to have only two functions, two callbacks. One is going to be in code. It's going to take a byte slice, and it's going to return a string and possibly an error. And another one is going to be the code. Or you know what, I'm just going to make it return only an error only a string, because for now we don't know if it's going to error out or not. And then we're going to pass a cookie, which is a string, and it's going to return a byte slice and an error. And I think that's good enough. And this was an interface, and now I'm going to define a concrete type, which I'm going to call HMAC-STORE.go. And this is package cookies, and I'm going to define this struct HMAC-STORE. It is not exported, and it's going to store a hash function, which is going to be of type function returning hash.hash, and we're going to store a key, which is going to be a byte slice. And then I'm going to define a constructor. I'm going to call it HMAC-STORE with a hash function and the key, which is going to be a byte slice. And then we need to verify if the key is of a valid length. So if length of the key, actually the length of the key in hash in HMAC there is no minimal length of a secret. So instead I'm just going to return like this. Actually I'm going to return an interface. I'm going to return this session store, and I'm going to return a pointer to this HMAC-STORE, and it's going to contain the hash and the key. And right now this isn't going to compile because we have not implemented these two methods on the HMAC store. And so I'm going to just define placeholder methods, and then we are going to use test-driven development to implement the actual logic on this type. So this is going to be the method encode, which takes a byte value and a byte slice and returns a string. So for now I'm just going to return an empty string, and then for this decode method I'm going to take a cookie, which is a string, and I'm going to it's going to return a byte slice and an error. So for now I'm just going to return an empty byte slice and an empty error. And then we can go ahead and write tests. So HMAC store test.go. Package cookies test, and then we can define a function called test HMAC store encode, which is going to take a testing.t, like so. Okay, yep. And store is going to equal cookies HMAC store, and we're going to need a hash function and a key. So the hash function is going to be SHA256 new, and the key has to be a binary. So I'm just going to hard code this binary in somehow in here. Yeah, for now I'll just generate a random binary, OpenSSL rand base 6432, and I'm going to copy it to the to the clipboard, and then I'm going to just store it as a global variable. So var key error equals base 64 std encoding decode string, this. And I'm going to use more like a global name for it. So this is going to be a signer. So okay. So also I think we could test both encoding and decoding in here. So the store is a store, and the value is going to be a binary that basically just says hello world. And so we can try encoding this value. So encoded cookie equals store, encode the value, and then we can assert, this is from the testify library, we can assert that the length of the cookie oh, you know what? We should not rely on the implementation details, like so. So I'm just going to I'm just going to assert it's not an empty. I'm just going to assert it's not equal to an empty string. And now if I run go test dash v, like so, then we can see that the test is failing because we haven't really implemented anything. Also, I'm going to write a make file so we can run the test with a simple command. It's going to be go test dash v /.. This will run tests in all files, like so. Okay, great. So now that we have a test, we can start writing some code. So cookie store, an HMAC store. So the encoding part. What we can do is we can take the value we want to encode, then sign it with an HMAC, and then we can concatenate the value with this checksum and then encode it as base 64. So this is exactly what I'm going to do, but I'm going to write a helper function to do the digesting part. It's going to be a method on the HMAC store, and it's going to be private, and it's going to return a binary as well. So mac equals HMAC new with the hash function and the key. Then mac write value return mac.sum nil, like so. So sum equals as digest value, and then we can just say, or you know what, I can just say it equals append the original value and the digest. So this is going to concatenate both binaries in one, and then we can return base 64 row URL encoding, encode to string sum. So now if I run the tests, the test is passing because the binary is not an empty string anymore. And so then we can build a next test. We can write the next test, which is going to be decoded error equals store decode cookie, assert no error, and then assert equals decoded and value, like so. Oh, okay, and I'm missing a T. So now if I run the test, it's failing because the binary returned by the store is empty because we have not implemented the store yet. So the first thing we're going to have to do is we're going to have to test we're going to have to decode base 64. So this is going to be base 60. I'm just going to call it bytes error equals base 64 row URL encoding decode string cookie. If error is not nil, return nil and error. and then we need to check the length. So what can happen is there can be three possible scenarios where things go wrong. One is going to be when the base64 is malformed. Then there is another when the base64 is like properly encoded, but the cookie is too short because it doesn't even contain enough data for a signature. And then what can happen is that the signature can be incorrect because it was tampered. So I'm going to also define two errors in here. Error malformed cookie equals errors new. The provided cookie is incorrectly encoded or too short. And then another error could be invalid signature. Provided signature does not match the expected value. Okay, so technically yeah, we can just return the base64 error for now. We don't really have to wrap it. And then we need to check the expected length. So the hash size can be calculated by taking the hash function and initializing it and using its size method. So I'm just going to call it size for now because we're going to be using this variable a lot. And if the length of bytes is less than size, it means that the cookie is malformed. Like so. And then we can split the message and the sum by slicing it like this: bytes, length of bytes minus size, and then bytes from the length of bytes minus size to the end, and then expected equals digest the message. And then you would expect that we could run something like sum equals expected, but there are two problems with it. Firstly, these are byte slices, and byte slices cannot be directly compared unless they are new. And secondly, we cannot just compare slices one by one using traditional methods if it's in a cryptographic context, because this is going to be vulnerable to the so-called timing attacks. So we have to compare these digests in a way that is going to take exactly as much time, regardless of how much of the sum is actually, how much of the values is going to be equal. Because like a regular comparison function, like a and b, would do something like for I equals 0, I is less than length of a, I plus plus, and then check if the length of a and b is different, return false. Yeah, so that would do something like if a of i is different from a b of I, then you return false, otherwise you return true. But you can do this with in a cryptographic context. So if it's traditional comparison, not safe in cryptographic contexts. So what we have to do instead is we're going to use XOR. Function const time compare. A and B are byte slices. And actually I'm going to call it const time equal because comparison means the meaning of comparison is more like comparing if something is less than or greater than, and we actually only care if they are equal. So firstly, we can keep this guard, we can keep this condition, but then for I equals 0, I is less than the length of I++, we're going to store this we're going to store the sum of our XORs in this accumulator, and then we can say the accumulator equals accumulator or A of I XORed by B of I. And what this means, what this operator means is that if any byte is 1 on the right, it will be stored in this accumulator. And the XOR is going to return all zeros if both bytes are equal, but it's going to return the difference if they are different. So basically this is going to accumulate the difference in any byte in any of these in any of those slices, and then we can just return if accumulator equals 0. And so then we can say if const time equal sum and expected, we can return the message and no error. Otherwise we return nil and error invalid signature. So now if you run make test, okay, this is still failing. And why is that? I think this may have something to do with this slicing. So I'm going to run it in a debugger. Okay, this didn't work. How can I run tests in DLV? Okay, I'm going to put a breakpoint on HMAC store.go line 61 and then run. Continue. Okay, so what is the size? What is the length of bytes? It's 45. Okay, so next, and then PMSG. Okay, I think this is kind of incorrect. For some reason what is the size of sum? Okay, I think for some reason we okay, why is that? If the size is going to be 13, how was this cookie formed again? We put the digest at the end, So this should be this should be okay. What's if I put it in a separate variable, what is this split? What is the size of a split? DLV test. So HMAC-SHA256 continue. What is the size of split? This is 13. So what's the length of a message? Okay. I think I swapped this slicing operators. This should be something like this, and this should be at the end. So now if I run make test, okay, now the test is passing. And what does it say in here? For loop can be modernized using range over int. Okay, for range a, I equals range a. Okay, make test. Okay, great. So in the test we can now decode the value from the decoded value and the encoded value, and then we could make some subtests. So I'm just going to, okay, this is the value, this is the cookie. Okay, t run happy path, and then this is going to take a function. So this is the happy path, and it can run, and then I'm going to define an example when the cookie is too short. So this is going to be another case. So the cookie is basically just going to be my 64-row URL encoding and encode to string, and I'm just going to write some gibberish. Yeah, I'm just going to write a string and encode it as base 64. So yeah, just hello, and then we assert that okay, yeah, we assert that there is no error. No, so if we try to assert that there is no error, we're going to get the first breaking test. So yes, we get an error, and we can now assert that there is indeed an error, and we can assert that the error is cookie error cookies error malform cookie, and then we can also assert that the actual assert empty, and the actual value is empty. Okay, great. So now we have an example of a cookie that is too short. And now what's going to happen if we pass an empty slice? So if we decode it, does it equal nil? Okay, so we can pass an empty value. Okay, great. And then what happens if we tamper the signature? So let's say we have okay, I'm going to take two cookies. Okay, I'm going to create a new store, and it's going to be cookies HMAC store with SHA256 new, and the key is just going to be hello. So if we create a cookie with this store, and the value is going to be I am a fake cookie, and we cannot really expect the cookie to be valid, right? So if we if we try to decode the cookie from another store, okay. Okay, let's just check if return value is empty, and the error assert error is T error cookies error invalid signature. Okay, great. So now we know that this cookie value, these cookies can be correctly encoded and decoded. So I'm going to commit implement HMAC store for cookies, and we're going to need a secret key base, and the secret key base is a long random secret with like a lot of entropy that we're going to be using to derive our secrets. For example, the cookie signer can be derived from a cookie secret with a key derivation algorithm. So in this envrc sample, I'm going to define another variable called secret key base, and I'm going to specify that you can generate it using OpenSSL run -base 64, and then if you remove new lines, and you can copy it in here. But okay, yes, so I'm going to generate a variable like this, run base 64, and you can see that there is a line break. So I'm going to remove the new lines, and I'm going to copy it to the clipboard, and then I'm going to open the actual envrc file I have in here. I'm going to copy this and this line, and I'm going to paste the binary I have just generated, and then in the configuration file I'm going to write a helper called must getEnv base 64 key string, and it's going to return a binary. So the value is going to be must getEnv with the key, and then decoded error equals base 64 standard encoding decode string value. If there was an error, log fatal f fatal could not decode environment variable with this name from base 64, and then we print the error. So this is the key and this is the error, and then we return the decoded value. Great. So now I'm going to move. So now in main.go, I have some secrets that I currently stored in here. I'm just going to move them all to the config package. This is going to be config, and 22 is also going to be config. And then the secret key base is going to be must get and base 64 secret key base. So now if I run derenv allow, we are getting a secret key base. Looks good. And now if I run the server, okay, we get a secret key base. And then I can specify the cookie store as the as another dependency of the router. Cookie store equals cookies HMAC store with the function SHA256 new, and then the key is going to be a derived value. So in config var cookie HMAC key equals argon2. Do I have argon2? Okay, we may not have argon2 installed in this package, so I'm going to run a go get-u, and then this argon2 is a key derivation function. I'm going to call the function called id key, and the first argument is a secret key base. Then the second argument is going to be a salt, which I'm just going to pass a string as cookie HMAC. And then what's next? I think the next is time. I always have to check OWASP password storage cheat sheet. And then with argon2 ID, we pass 46 megabytes of memory, time 1, parallelism 1. Okay, so this is okay. Time 1 memory 64. Okay, so time 1 memory is going to be 64 megabytes and parallelism of 1, and then the length of the HMAC key is going to be 32. This is a lot of positional arguments, but once you get the gist of key derivation function, it's not really that terrible. And this function we can also use later on to store digested passwords. And then back in main.go, I'm just going to pass the HMAC key in here. And then the router, it's going to take a cookie store, which is going to be cookie store. Wait, cookies session store, like so. And then we don't really need it for now, but at least we know that we have it for later. Okay, great. So we can see that the website still renders. We are not currently using this session store, but we're going to use it in the next video. If you enjoyed this video, you can consider joining my Discord waiting list at discord.moros.dev, and if you like this video, consider clicking like and maybe even subscribing. This way I can become monetized quicker. And thank you for watching, and I will see you in the next video. Goodbye.